Hey everyone, so in this video, this will be our final video on the Coulomb's law series, in which we'll just cover a few word problems and real-life scenarios dealing with the applications of Coulomb's law. So far I've only explained the scientific phenomena behind Coulomb's law, but now I'm going to relate it to real-life scenarios and real-world applications in the technology industry field. So yeah, let's get started. So number one, Cisco, a networking hardware and software company, recently created a new telephone as shown below. Below is a RJ11 cable used to transmit signals between copper wired network and a telephone user. Calculate the magnitude of the electrostatic force between charges 1 and 2, given the information about them and their position. So here's Q1, here's Q2. They're both oppositely charged, one's positive, one's negative. They're separated by about 0.8 meters. Q1 has a magnitude of negative 0.04 coulombs, and Q2 has a magnitude of 0.07 coulombs, positive 0.07 coulombs, and we can just plug in their values into the Coulomb's law equation, which is the electrostatic force equal to K times Q1 times Q2 all divided by R squared. Plugging in K will yield 9 times 10 to the 9 newton centimeter squared all divided by Coulomb squared. And Q1 is 0.04 coulombs, and Q2 is 0.07 coulombs, and the R is 0.8 meters. And we don't need to convert anything since we're given in coulombs. We're given the unit in coulombs. We are not giving it in microcoulombs or nanocoulombs, so we don't need to convert. And I'm plugging in 0.04 coulombs for Q1, not negative 0.04 coulombs, since we're just finding the magnitude of the force, not the vector, so we can just neglect the negative sign. So this will just simplify to 9 times 10 to the 9 newton centimeter squared times 2.8 times 10 to the minus 3 coulomb squared, all divided by Coulomb squared times 0.64 times meter squared, in which meter squared and Coulomb squared cancel each other out, leaving us with the electrostatic force equal to 9 times 10 to the 9 newtons times 2.8 times 10 to the minus 3, all divided by 0.64, which yields a value of 3.94 times 10 to the 7 newtons, approximately. So that's the magnitude of the electrostatic force between these two charges placed in this RJ11 cable. So within this RJ11 cable, these two charges will be stationed about 0.8 meters, and yeah. So data is obviously flowing when when electrons within these charges are within these atoms are moving between one another, and that's how data is transferred between a copper wire network and this RJ11 cable through the telephone and to the telephone that we obviously use to talk with one another. So yeah. So here's the next problem, another word problem, real life scenario with Arduino this time. So Arduino, an integrated electronics and computer science based platform, recently developed a circuit board with 3 LEDs erected on it, mimicking a traffic light simulator. At the port where you can plug in a power source, Arduino electricians wanted to calculate the electrostatic force between 2 electrons positioned near one another. Can you help the electricians out by calculating this value for them? So here's where you would plug in obviously the battery or power source, and here these red and blue wires is where the electricity would travel into this board and obviously cause these LEDs to light up. So here's Q1, here's Q2. Both are like charges, negative charges. They're both electrons. They're separated by 3.4 nanometers. So we haven't dealt with nanometers or the nano unit at all in this video or in the series, but just know that micro is 10 to the minus 6 and nano is 10 to the minus 9. Just keep that in mind. So Q1 is negative 1.6 times 10 to the minus 19 coulombs, and Q2 is negative 1.6 times 10 to the minus 19 coulombs. So here's the Coulomb's law equation. Electrostatic force equal to K times Q1 times Q2, all divided by R squared. Electrostatic force equal to 9 times 10 to the 9 newton centimeter squared, all divided by Coulomb squared, times 1.6 times 10 to the minus 19 coulombs, times 1.6 times 10 to the minus 19 coulombs, all divided by 3.4 times 10 to the minus 9 coulombs, or meters squared. So here what we've done is, here's a new format of writing exponents in scientific notation. Rather than having to write out times 10, right? We can just, that times 10 portion of the scientific notation, we can just replace with e. And then whatever power we're raising it to, we can just write after it. So 1.6 times 10 minus 19th power is the same thing as 1.6 e to the negative 19th. And 3.4 e to the negative 9th, or 3.4 times 10 to the minus 9th meters, which is 3.4 nanometers. We'd plug in for R. So just a little bit of simplification, this leads to electrostatic force equal to 9 times 10 to the 9 newton centimeter squared, all divided by Coulomb squared, times 2.56 times 10 to the minus 38 Coulomb squared, all divided by 1.156 times 10 to the minus 17 Coulomb, or meter squared. So we can see the meter squared and the Coulomb squared cancel each other out, as they're both the numerator and denominator of this problem. So now we're just left with the electrostatic force equal to 9 times 10 to the 9 newtons times 2.56 times 10 to the minus 38, all divided by 1.156 e to the negative 17, or times 10 to the minus negative 17. And this should yield us a value of 1.993 times 10 to the minus 11 newtons as the electrostatic force between these two charges. That's just the magnitude, okay? But if we were to find like the electrostatic force on one of the individual charges, they would be in opposite directions, right? Since they're like charges, they're both negatively charged, they're going to repel each other. Electrons will repel each other if you bring them closer to each other, or bring them closer to each other. Just like if you were to bring two south poles of a magnet next to each other, they would repel each other. So yeah, this is like the application in a real life scenario, because with like with electricity traveling in like a circuit, so obviously electrons are going to be like moving from an atom to another atom to another atom and so on. That's how electricity is obviously generated, which is current. So electrons near each other in their valence shells will obviously experience some kind of repulsion because of their proximity. So as shown here in this example. So yeah, this is an example of a real life scenario that you might deal with as an electrician. So that was fun to work with. Alright, thank you guys so much for watching this entire series. I hope you enjoyed it. And if it did seem kind of confusing, please go back and watch the videos, because they really are helpful in understanding these kind of like problems you might deal with in physics, or in like AP physics if you take it. But it's just a fun lesson to learn and get into electronics if you're new to electronics. It's a fun way to enjoy it. And I hope you guys enjoyed the series once again. If you really got stuck on a topic, please feel free to go back and watch it as many times as you need to. Pause, take notes. It's all up to you. And yeah. Anyways, thank you for watching and have a great day.